Thank you, Steve. So hello, everyone. I'm going to give you an update on my attempts together with Subrat Razu and the collaborators to reconstruct the interior of a black hole from the conformal theory. So the main question we want to understand is whether a big black hole in ADS has a smooth interior and whether the CFT can describe it. And at first sight, you might think that the answer is obviously yes. But we have seen arguments in the last years which speak against this, the smooth interior for a big black hole. And one of them is the strong subadditivity paradox, which was pointed out by Matur and the AMS collaboration some time ago. And perhaps more relevant for the ADS black holes, the arguments which have been developed in this paper. So it's Douglas together with AMS. And another paper by Don and Zhou, where specific counting paradoxes were formulated, which seem to suggest that it is impossible to have a description of the black hole interior in ADS-CFT. On the other hand, with Subrat, we provided an explicit construction of the interior of a black hole from the CFT. So I would like to explain how this construction is able to avoid the paradoxes. And as I will try to emphasize, the important element is that in this construction, we allow the operators inside the black hole to be state dependent, to depend on the microstate of the black hole. And finally, I will, if I have time, I will review recent progress, which is based on the two papers that I wrote with Subrat this year. So let me start with a reminder of how the reconstruction of ADS of the region outside the horizon works in ADS-CFT. We start with a big black hole in ADS, and we take a free scalar field, which in effective field theory can be expanded in terms of modes. And so we have some creation and annihilation operators multiplying wave functions. And these modes have to obey canonical commutation relations. And moreover, at late times, when the black hole equilibrates, we expect from effective field theory that these modes are thermally populated. So how do we reconstruct this from the conformal field theory? In this case, it's not very difficult. And the construction is based on the work of many people. And the main idea is that we take a single trace operator O in the CFT, which is dual to the bulk field phi. Then we consider the Fourier mode of the single trace operator in the conformal field theory. And we simply identify the Fourier modes of the boundary operator to the creation and annihilation operators of the field in the bulk. So in this way, you can write down an expression for a local operator in ADS in terms of a smeared operator on the boundary of the CFT. Now, I think this is not very controversial. I mean, most people agree on this. And even though there are interesting subtleties about the behavior of this construction at large angular momentum and questions about gaze and diffeomorphism invariance and how we can deal with one-over-n corrections. Now, the main question we want to discuss is what happens when we want to go inside the horizon. And you can see that from effective field theory, we need a new set of modes that I call B tilde, which are the right-moving modes on this diagram. And these modes B tilde have the property that, according to effective field theory, that they have to commute with the modes outside the horizon. And moreover, if we want the horizon to be smooth, they have to be entangled. And so far, we have identified the modes B with the operator O in the CFT. And the central question we want to address is what is the meaning of the operators B tilde from the point of view of the conformal field theory. Now, as I mentioned before, there is an argument given by AMS that such operators cannot possibly exist in the conformal field theory. And the argument is based on the algebra that these operators satisfy. So within effective field theory, the operators behind the horizon obey the canonical commutation relations. However, they have peculiar commutation relations with Hamiltonian. So in particular, this guy, B tilde dagger, which is the creation operator for a mode behind the horizon, seems to lower the energy of the CFT Hamiltonian. And in this paper, it was argued that this algebra is inconsistent with the spectrum of states in the CFT, and as a result, the operators B tilde cannot possibly exist in the conformal field theory. So let me remind you how the argument goes. From the canonical commutation relations, we see immediately that B tilde dagger acts like a creation operator, which means that B tilde dagger should not annihilate typical states of the conformal field theory. On the other hand, from this commutation relation, we notice that B tilde dagger lowers the energy of the CFT. So it maps CFT states of energy E to CFT states with energy E minus omega. However, in the conformal field theory, the entropy is monotonically increasing with energy. So this seems to suggest that an operator maps a bigger Hilbert space into a smaller Hilbert space. And if B tilde dagger is an ordinary linear operator, then it means that it must necessarily have a non-trivial kernel. And this statement is inconsistent with the statement that B tilde dagger should not annihilate typical states, and hence B tilde should not exist in the conformal field theory. So this is a very, I think it's a kind of robust argument, and we have made it a little bit more precise by formulating it in terms of two-point function in our recent paper. There are also related arguments, like an argument based on the trace of the number operator for the infalling observer, which was formulated by Busso and Maros-Polzinski. And more intuitively, perhaps, there's a statement about the entanglement in the conformal field theory. So if B tilde is a fixed linear operator, it is very hard to imagine how, for typical states of the conformal field theory, we would have the correct spatial and particular entanglement that we need between B and B tilde in order to have a smooth interior. So all of these arguments suggest that the black hole in ADS does not have a smooth interior. And in my view, at least, this is the most well-defined version of the firewall paradox. And then the question is there a way out of these arguments? So let me now review the construction that we developed with Suvrat on the operators in the interior of the black hole. So the starting point is that we want to concentrate on something that we call the small Hilbert space H of psi, which is defined in the following way. We start with a black hole microstate, psi, and we have an observer, a bulk observer, who wants to perform experiments at around time t equals 0. And then we want to consider all possible experiments that this observer can perform within effective field theory. Now, in order to describe these experiments, we do not need the entire Hilbert space of the CFT, but rather the small set of states which can be produced by the state psi by acting with the fields that the low-energy observer has access to. For example, if phi is a bulk scalar field, we want to consider states where we act 1 time, 2 times, 3 times, a fixed number of times on the state psi, and then also consider all possible linear combinations of states of this form. So I want to argue that all experiments all simple experiments within effective field theory will take place within this space.
Is little n fixed here? Or?
Yeah, so little n does not have to be fixed, but what is important is that this little n does not scale with capital N, where capital N is the rank of the gauge group in ADS-CFT.
You're not allowed to, you don't need Wilson loops.
Well, yeah, I want to describe a bulk theory where the stringy effects are small. Yeah, so I want to study the supergravity approximation.
Is it clear that that experiments where it does scale with capital N can't be performed within effective field theory?
Yeah, good. That's a good point. That's a good point. Of course, there are experiments within effective field theory which need operate with, for example, if you have the 2 black holes which merge and form a bigger black hole.
Yeah.
Okay, that you can describe in effective field theory, perhaps.
Or the radiation passes
Sure.
through a cloud.
Sure. So I'm not going to deal with these experiments because they're more complicated. So this is a more difficult question that I'm not able to answer at the moment.
Okay.
Yeah. So I think already at this level we will have disagreements. So maybe we can just stick to this one for now. So let me now translate the statement in a CFT language. We want to take a CFT microstate. So it's a typical quark-gluon plasma state. And since we explained before that the field phi, the bulk field, is related to a single trace operator O, we want to consider the algebra, which is constructed by taking a small number of single trace operators and multiplying them together, and then taking all possible linear combinations. So I define this object, this small algebra A, which is defined by inserting the single trace operators within a time band which is not too long. And I introduce some kind of cutoff in the number of operators that I multiply together. So this has to be regulated. So it's not strictly speaking an algebra, because it has to, you cannot arbitrarily multiply single trace operators. But the results of what I'm going to say does not depend sensitively on this cutoff. So from now on, I will refer to this as an algebra.
This is acting on either a small or a large black hole, or is it essentially
Fixed.
one or the other?
Well, right now, I have not made.
Plus compared to ADS.
So this black hole is going to be a big black hole.
It has to be big.
Yeah,
Okay.
that's right.
So these points are averaged out or something?
Yeah, so these points have to be smeared a little bit so that the energy is finite. So I have to introduce some UV regularization.
Normally, if you take a slice, so this red band there, that's a belt, that's a time slice, right?
Yeah. No, it's long, right? It can be, this T can be, let's say, it can scale with n, or it can be, yeah.
But why don't you generate the algebra of all operators?
Yeah, because I'm talking about small products.
Because it's single trace, you don't generate everything?
Yeah, there are single trace, and I'm considering small products. Where small, I mean that the number of factors does not scale with n.
Oh, you would put a limit on the number.
Yeah. Actually, I will come back to this point later in my talk, and I will explain in more detail. But yeah, roughly speaking, the number of factors in the product does not scale with n.
It's not exactly an algebra.
Yeah. It's not an algebra. That's why I have this. Yeah, it's not really an algebra.
For regularization, and because you
Yeah,
limit the number.
yeah, that's right. Yeah.
You probably also want to smear against basically low frequency data or something.
Yeah, that's because of this. That is achieved by taking this band, which is finite. So I do not allow operators which are separated by a very long time scale.
Yeah, but you could take O and smear it with a very high energy thing.
Yeah,
and
and then I have this.
okay.
Yeah.
That's all right.
And
Yeah.
so I should think of capital T as being order 1 also?
No, well, okay. Later in my talk, I will talk about a situation where capital T is order 1. But in that case, there will be no black hole. I will only have empty ADS. So that's a different kind of computation where the same regularization will be useful. In the case where we have a black hole, I want to think of this capital T as being probably over there the scrambling time.
Okay.
Yeah.
I have another question. Sometimes you can have theories that can be expressed in terms of basic operators in very different ways. If you distribute model like the Turing model,
Mm-hmm.
So in some representations, the basic what is the basic field in one representation, talking about bosonization and things like that, they look at a very non-polynomial expression in the field in another representation. I'm a bit worried about what's the invariant concept.
Yeah, okay, to simplify the, okay, okay.
Statement that there's only a finite number of factors.
Yeah, in the case of the large N-gauge theory, there's a very natural hierarchy between single trace operators and operators whose dimension scales with n squared.
So you have in mind particular gauge.
Yeah, of course. So this, So all I'm saying is relevant for a large N-gauge theory, which has a holographic dual. So now, what we have to define, what we want to define now, is the Hilbert space, this small Hilbert space, which is defined as the span of states that you get by acting with elements of the small algebra on the state psi, which is the black hole microstate. So here is the Hilbert space of the entire Hilbert space of the CFT, and I'm concentrating my attention on a subspace, H of psi. Again, this is the subspace that you get by starting with a quark-gluon plasma microstate and acting on it with a finite number of single trace operators. And I argued before that simple effective field theory experiments in the bulk will take place inside this subspace. So the operators behind the horizon, B tilde, that we need, these interior operators, will be defined to act only in this subspace. This will be very important. And this is intuitively, you can think of the subspace perhaps in a similar way as the code subspace, which was mentioned in this program some time ago. But in our case, the space H of psi is not related to quantum error correction in any direct way. So let me also emphasize a very important point, that even though we got the subspace by acting with simple operators in the conformal theory, I want to make the claim that this space already contains states in which the black hole interior has been excited. So these are states that you would get in the bulk by acting with operators B tilde in the interior of the black hole. Now, you may find this a bit surprising, but it's not very unusual. It happens often when we have entanglement. So even in ordinary quantum field theory without gravity, this fact is related to, let's say, the Risch-Leader theorem, which claims that if you take a small part of Minkowski space and you act with operators within that small part, you can reconstruct a dense set in the Hilbert space. So what we want to argue here is that the state of the CFT seems to be in an entangled state relative to the single trace operators, and as a result, just by acting with the single trace operators, you can reconstruct the Hilbert space, which includes excitations behind the horizon. All right, so these CFT operators that we're looking for, which correspond to B tilde in the bulk, will act on this subspace, and we will call them O tilde in the conformal field theory and refer to them as mirror operators. Now, a very important thing is that these operators O and O tilde have to commute, because in the bulk, O are operators corresponding to the exterior of the black hole, and O tilde corresponds to the interior.
So, sorry, Kyriakos,
Yeah.
can I just ask,
Yeah.
do you mean that to leading order in 1 over n, or to all orders?
To leading order in 1 over n. Yeah. So, yeah, significantly more difficult to settle what the commutators should be at subleading order, and then it also becomes important, what becomes important is the difference between B tilde and O tilde. So, we have to be careful about how to relate bulk data to boundary data.
Right.
So now, it's a little bit surprising what we said here, that we can define operators O tilde acting on the same Hilbert space which commute with the O's. And in fact, if you think about it a little bit, you can ask yourself, can we do the same thing around the ground state of the CFT? And then the answer is clearly no, because in the ground state of the CFT, we know all operators which are relevant at low energies, and we know there are no operators O tilde which commute with all single trace operators. So what is qualitatively different in the case where we have a black hole? So what is special when psi is a black hole microstate, which allows this small Hilbert space, which is defined as the span of the small algebra acting on psi, to be big enough to accommodate the action of operators O tilde, which commute with O? And I will try to argue that the main qualitative difference can be summarized by the following statement, that if you take a typical black hole microstate and you try to annihilate it by elements of the algebra, it is not possible to do this. So there is no simple combination of single trace operators which can exactly annihilate a typical quark-gluon plasma microstate. And I want to argue that this is a central point for the construction of the tilde operators. Yes?
Sorry, I had a question about
Yes.
the previous thing.
Yes.
You said if we expand around the CFT vacuum,
Yes.
then there's no operators that commute with all local operators, or with all low-dimension local operators. But probably a leading order in 1 over n, there are such things, right?
Like?
Well, like the things that Joe and Vlad and Eric had in their model, right? Those were examples of operators that...
Those are non-local, though, right? So, of course, the
That's
bulk
right,
annihilation
Yeah,
operator.
but those will
that's not
have
what he means.
effectively a large conformal dimension, right? At least, I think it will scale like
The
a
statement was
lambda.
There's no O tilde. But so what you want to say is there's no... What is the precise statement about... So expanding around the CFT vacuum?
I will make the statement a little bit more precise. So the precise statement is that if you look at the representation of the algebra A on this Hilbert space.
But no, we're not. I'm talking about your statement around the CFT vacuum.
Yeah, that's what I'm saying.
Okay.
So if you look at the same Hilbert space constructed around the vacuum, you will find that this representation is irreducible. So there are no operators which commute with it. And
no operators at all.
well, low-lying operators with, let's say, energy of order 1.
That act within the subspace.
That act within the subspace. That's right. Yes.
So, from the viewpoint of this Tomita Takasaki theory, I think it's simply the statement that if your state isn't pure, then you're on the representation.
Precisely. I will come to exactly this point in 2 slides. Yeah. Right. So let me also give a physical. So again, the important element, the reason that we have a qualitative difference between the black hole and the ground state is that in the case of the black hole, we cannot annihilate the state by acting with simple elements of the algebra, In the case of the ground state, you can definitely write down annihilation operators. If you take the CFT on the sphere and you act on the ground state with this operator, then this is equal to 0. So you can annihilate the ground state. But in the case where you have a black hole, this is not possible. And I will try to argue that the physical interpretation of this statement is that the state psi appears to be entangled when probed by the algebra A. So I phrase it in this slightly unusual way because, usually we talk about entanglement when we have a decomposition of the Hilbert space. But in this case, it's not so clear. So what we have now is an algebra acting on a state, and we want to find a way to encode the statement that this representation of the algebra on the state corresponds to some sort of entanglement. And I'm saying that this is one way to phrase it mathematically.
Suppose you have a black hole that's just under the Hawking-Page transition, so it's not a black hole, it's just the thermal state. Would that statement also be true about
it could be true that if you take I guess you want me to think of some hot star in ADS, which is very complicated, and So I think if the state is chaotic enough, the statement will still be true, and you may still be able to define these operators. Yeah. But
they won't have the right expectation.
Yeah, they will not have the right expectation values to reconstruct a smooth interior. But the fact that the representation will be reducible will be true, I think.
So I don't have annihilation by, well, my black hole is sort of over here, and I have basically annihilation operators that sort of live over here.
I don't think you can do that, right? It's like the Risch-Leader theorem in flat space, that you cannot write down annihilation operators in a localized region.
Do an approximation.
Do an approximation, yeah.
Okay.
Yeah.
You think that? Well,
Yeah, I think that's relevant. And yeah, so yeah. Okay, I don't know if I will have time, but if I get to the end, I will come back to you. So, okay. If you want, I can explain a little bit more why this statement is related to entanglement, but maybe it's obvious to people. So,
do you think that statement will be true when the black hole is evaporating? I mean, not for...
Well, in ADS, it's a little bit hard to think about what will be the end point of... I mean, a big black hole will not evaporate, so... you want to think of a small black hole in ADS?
When you have a pure state and it evolves into a black hole.
Yeah, I think that before you form the black hole, probably this statement is not true in the sense that if you have a collapsing shell, it will probably be easier to find annihilation operators. But after the black hole forms and the theory deconfines, I think it will be different. Okay. So, okay, I can explain if you want more why entanglement is related to this property, but maybe should I explain it, or it's kind of obvious, okay? So let me now come to the proof that whenever we have a small algebra acting on a Hilbert space with a property that the algebra cannot annihilate the state, then the representation of the algebra is reducible, and the algebra has a non-trivial commutant acting on the same space. Actually, the proof is very simple. You just define an antilinear map acting on the space by this equation. And then you define this map S, which take any state of the form 8 psi into 8 dagger psi. And then we define operators A hat by conjugating the operators of the algebra by S from the left and the right. And then it's a trivial exercise to check that this object commutes with all elements of the algebra.
In the subspace?
In the subspace. Here is the proof. You just follow the definition, and then, okay, following these two lines, you can prove that the commutator of any element of the algebra A with any element which has been conjugated from the left and the right by this object S has a commutator which is 0 when acting on this subspace. So these operators are almost what we need for the interior of the black hole, but not quite, because if you compute the 2-point functions between A hat and A, they don't quite have the canonical form that we expect from the, let's say, Hartle-Hawking state. And there's a nice construction which allows us to fix this problem, and it is inspired by a mathematical theorem, which is useful for the classification of von Neumann algebras.
I'm sorry, can I?
Yeah.
It seems essential that the A's are not Hermitian for this to work. I'm confused why I couldn't just take a basis of Hermitian operators.
Well, this is an antilinear map, so you can certainly choose a basis of Hermitian operators, but
Sorry, if A was Hermitian, S would be the identity.
Right.
That's what's confusing.
No.
The imaginary part will have an I in it, and then this S is antilinear, so it'll flip the sign of the I.
Yeah.
I understand that, but
yeah.
That's got to be the resolution, right?
Yeah. So now, what I was saying is that this mapping S is not really an isometry, and this mathematical construction gives you a way to redefine these operators a little bit. So we define the magnitude of this map, S dagger S, and then we take this guy S and we divide it by the square root of delta in order to make it anti-unitary. And here is the final expression for the operators that we will eventually use for the black hole interior. Now, to prove that this guy commutes with the original operators is a little bit more work, because what I proved before is that this operator commutes with the elements of the algebra. So to prove that this one continues to commute takes a few more steps, but it can be done. And this operator delta that I defined is an operator which is positive and Hermitian, and it can be written as the exponential of some Hermitian operator, which is usually called the modular Hamiltonian. Now, if you are familiar with the notion of the modular Hamiltonian in the case of entanglement, where we have a bipartite system and we cut it in two and we look at the reduced density matrix on one of the subsystems, and then define the modular Hamiltonian as the logarithm of the density matrix, you can check that this definition of the modular Hamiltonian coincides with the usual one. But it's a little bit more general.
But
yeah.
It has the one modular Hamiltonian in some region and the opposite in the other, right? It doesn't
yes.
limit on only
yes.
one.
Right. So if I define the modular Hamiltonian in this way, then this K acts on both A and B. So I have to evaluate K restricted on A to make contact with the usual modular Hamiltonian. So to say it more physically, if we do this construction in a Minkowski space, this will be the Lorentz boost acting on both sides of both Rindler wedges, not just a half of the boost. Anyway, so now in the case of the large N gauge theory, and if you use the KMS condition and large N factorization, you can show that for a typical black hole microstate, this modular Hamiltonian is simply proportional to the CFT Hamiltonian. So then you can plug everything in, and you get this formula for the operators for the interior of the black hole. So you get a set of linear equations that the operators of tilde have to obey when acting on this subspace. So O tilde, when it acts directly on the typical black hole microstate, it acts as if the minus beta omega over 2 times of dagger. However, if it acts on a state where we have already excited it with a couple of insertions of O, the rule is that you first commute it to the right, and then you let it act according to the first formula. And what is a little bit important is to emphasize that the commutator of O tilde with Hamiltonian is similar to the one that was found from effective field theory by Amses in a few slides ago, right?
Sorry, so that commutator is so now that's a 1 over n correction,
correct.
Right?
Correct.
So it, I mean.
Yeah, so we need some
consistent for you to say that commutator with also telling me what the O and O tilde commutator is.
I think as we have discussed many times, I think this commutator is enforced on you if you look at states which are this sharp microcanonical ensemble.
No. But what I'm asking is, I don't see the point of discussing that commutator if we're not going to give a version of these rules that includes the prescription of the 1 over n.
Right. So this commutator is you have agreed with your point. So in principle, we would like to find the 1 over n to define the 1 over n corrections to all of these equations. However, this particular commutator will play an important role in what follows. That's why I have demanded that these operators have to obey this particular commutator with Hamiltonian.
So you can.
I just demand this commutator.
But then you haven't really fully specified.
No, I haven't fully specified it at the level of 1 over n. That's for sure. I have not fully specified the operators at order 1 over n.
So, for example, with this choice of the commutator, you would not be able to say that O and O tilde commute at next to leading order.
Yeah, I do not want to make any statement about the next to leading order because I do not have an algorithm to define these operators.
For example, had you chosen it to be 0, then you could consistently choose O and O tilde to commute.
Right, but I have a different reason to expect that this commutator will be non-zero in the case of the Hamiltonian. That's why I want to insist on keeping this commutator non-zero.
This has to do with narrow states,
right? Precisely.
Yeah.
And also with what you get from the bulk, right? I mean,
well, so for narrow
it
states,
also has to do with, sorry, just a moment. It also has to do with.
Maybe I'll postpone this until you talk about it. But,
this is what you get from effective field theory, right?
Well, no, that commutator depends on how you define B tilde.
Yeah, of course,
it has to do
exactly.
With gravitational dressing.
Right. So precisely. So I want to define these operators relationally relative to the right boundary.
Yeah, and then.
So I throw an observer from the right side, let the observer fall in by measuring a certain amount of proper time, and that's the dressing that I want to use.
Yeah, but then if you choose to dress them that way, then you must also have the O tildes not commute with the O's.
That's very possible. Yes.
So then using this, okay, I made my comment.
But that's a 1 over n correction.
Yep.
What?
That's a 1 over n correction.
That's right.
This commutator is a 1 over n correction because the relationship between H and the stress tensor has an n squared in it. So this is a 3-point function. So here he's putting in some rule about the 1 over n
That's right.
corrections.
That's right.
Without telling us about the other 1 over n corrections.
Right. So this story about Tomita Takasaki and this exactly this this existence of a non-trivial commutant is really a very general story that applies whenever you have
part of a consistent
state which isn't pure. For example, it applies when you just take a thermal state of Minkowski space. Your commuting systems are the tilde. So what is specific to the black hole?
Nothing. Even in that case, you can still define these O tildes. But as Dan pointed out before, if you look at the correlators between O and O tilde, in that case, there will be no way that you can combine them together and reconstruct a smooth space-time. So
I understand that in this case there is just one. I mean, this is just a field theory. There would be just one space-time. But what is specific to the black? I mean, what is specific? What is it about the state psi there that?
Well, there's a one consistent. So there's one condition.
Black hole rather than some generic non-pure state.
Well, there's a consistency condition which is necessary, which is that you cannot annihilate the state with elements of the algebra.
So that's just saying that it's not pure, basically.
Well, it's not pure as seen by the algebra. Fundamentally, it is a pure state.
There are many states of that.
Yeah. So I'm saying.
What is it that makes them?
Well, this kind of definition of the tilde operators you can perform in any situation where you have a chaotic quantum mechanical system that you are probing with a small algebra. Okay. Whether these operators are useful in order to reconstruct a smooth interior spacetime is a different story. It has to do with the correlation functions of these operators with O's.
Well, maybe.
Sorry, can I? Yeah. So, could I, as a simple example, could I take just pure ADS and Rindler coordinates?
Sure.
So then I have the right boundary and the left boundary, and I could do all of this stuff, right?
Yes.
And nothing would go wrong.
Yeah. So I think
the conclusion would be like operators on the left side you can rewrite as operators on the right side.
No,
not on the right side. There will be operators acting on the space, but they cannot be rewritten as operators acting on the left side necessarily.
I mean, there are operators that annihilate the vacuum in that situation where you just combine operators on the left and the right.
Yeah, but I think Ben is talking about the situation where you restrict your algebra to only, let's say, one wedge, right? Or am I wrong?
Yeah, I mean, isn't that like what you're doing here?
Yeah, this can be done certainly, yeah. and I will come back to this later in my talk. Yeah. Okay, so now using these O's and O tilde that we defined, you can reconstruct the bulk field, and if you evaluate, so you can reconstruct the bulk field by convoluting these guys with wave functions, and then if you evaluate low point functions of these operators, then you can check that they reproduce to leading order in large N, the effective field theory in the interior of the black hole, and in that sense, we declare that there's a smooth interior and nothing dramatic happens when an observer crosses the horizon.
But that actually would have been true for the other choice of the Hamiltonian too.
Yeah.
The commutator. Because
I'm not sure about that.
Because that's a 1/n correction. So.
Yeah, but I'm not sure that if you take that choice for a, you mean for a state which is in a microcanonical ensemble?
No, I mean for these other states.
So I think for the microcanonical ensemble, this is the only choice which is consistent. All right. So before I go on to some new stuff, let me mention that this construction is, in some sense, a realization of the idea of black hole complementarity in the sense that these operators O tilde that we constructed seem to commute with the O's. But so the fact that this commutator is 0 is in reality an approximate statement because it was constructed to be 0 only when acting in this small Hilbert space H of psi. And if you really want to think about the fundamental commutator between O tilde and O, then you can also consider, let's say, n squared point functions. So you insert many operators O, which takes you outside your algebra A, and then you will discover that this construction that I described completely breaks down, because you can certainly annihilate a black hole microstate if you act with a complicated enough operator. Or relatedly, you can discover that O and O tilde fail to commute inside complicated correlators. Or equivalently, we can rewrite O tilde as extremely complicated combinations of the O's. So the idea is that we have the observables outside the black hole, and if you use very complicated measurements in the exterior, you can reconstruct the operators which are in the interior. So it is important to distinguish between simple and complicated experiments. And what I'm saying is that the decomposition of the Hilbert space in quantum gravity as the interior times the exterior makes sense for simple experiments, but may break down for complicated experiments. Now, I claim to have a construction of the O tilde operators for the interior, even though there was a no-go theorem pointed out by Amsterdam and other people. So how is it possible? The answer is that the construction that I described is characterized by something that I call state dependence, which means that the operator tilde were defined to act as linear operators only on a small Hilbert space defined around a given initial microstate. So remember, these operators were defined only on the subspace H of psi. If you take a different microstate of the black hole, even if it has the same mass, so even if it looks like the same black hole from the exterior, you will construct a different small Hilbert space, and then you will construct a different linear operator tilde relevant for that microstate. And then an obvious question is it possible to stitch them together, all of these guys, into a globally defined linear operator? But the answer is clearly no, because there are too many states. There are e to the s states, and then the overlaps between different subspaces H of psi become too large, and then you can check that, it's not possible to promote these operators into fully globally defined linear operators on the Hilbert space. Well, this is the result of the counting arguments that I mentioned. However, it is okay to do it if you have a small subset of states.
So what does okay mean?
You can find, right, so suppose you have two different microstates, black hole microstates, psi 1 and psi 2. And, okay, just to avoid some technical complications, let me take this psi 1 and psi 2 to be typical uncorrelated states. So I have this subspace H of psi 1, H of psi 2. And what I'm saying is that I can define an operator tilde which acts on...
yeah, but that's certainly true.
Yeah. So just for everyone, I can define an operator which acts on the direct sum of the two subspaces. And when you restrict the operator on the individual subspaces, they reproduce the results that we had in the beginning. Okay. So the fact that state dependence resolves these arguments is kind of obvious. I mean, I think there's no disagreement with that in the sense that these arguments were based, it was a fundamental assumption that the operators in these arguments are normal linear operators defined globally on the Hilbert space. So this counting argument and the trace argument do not apply if I am allowed to change the operator as a function of the state. And also, if you allow the operators to depend on the state, you have a natural explanation of why you get a correct entanglement for typical states. The explanation is somewhat trivial in the sense that we select the operators B tilde by the entanglement, so obviously they will have the right entanglement. Now, this type of state dependence is not very, it's unusual in fact. We do not know any other example in quantum mechanics where we have this type of state dependence. And an interesting question is whether this has to do with a black hole interior or whether it has to do with quantum gravity in general. So for example, it's not clear whether you can find operators with a state independent outside the horizon. So in the beginning, I told you that there is a construction to, a way to reconstruct points in the exterior of the black hole. However, the constructions that have been written down in the literature all depend on the states that we're talking about.
No, they depend on the field. They're not. They're linear operators. When you say state dependence, you mean a nonlinear operator.
Yeah.
It's certainly not. It's a misuse of words to call it state to use state dependence.
Yeah, I didn't say that. I said that. First of all, I think there is no explicit check that this operator can be promoted into a linear, globally defined operator, which will reproduce this HKLL operator on any individual state, especially if you start talking about time-dependent black holes rotating. And
there's not a complete discussion. Yeah. There's no evidence that it's not.
Yeah, I agree. I didn't want to make any statement.
Much evidence.
That I agree. I just want to say that I am personally agnostic about this statement. So, yeah.
Well, maybe I'll just make two comments about that. Yeah. One is that in simpler theories like electrodynamics, there are similar phenomena that happen where you really know that it's a state-independent operator. But then also in the discrete models that I talked about in my talk here before, you can see very explicitly that whenever the operators in the exterior make sense, they're good linear operators.
Fine. I didn't want to make the statement that the black hole exterior has to be state-dependent. Okay. I just wanted to say that it's a discussion which has not been fully clarified, in my opinion, in the literature.
But just to be clear, if you had a sufficiently complicated state, one of these, stars in ADS or something like that, your construction would still go through and let you define, quote, interior operators.
Yeah, I think if there's a natural way to define a small algebra relative to the entropy of the state, you would be able to define these tilde operators, which have the right correlators.
So what would your interpretation be? That they're just not physical or not?
No, it's like asking if you take 2 copies of the n equals 4 below the Hawking phase transition, you can still think about the thermofield state, but you cannot reconstruct anything that looks like an interior. So you still have 2 copies which have similar algebraic properties as the ones in the black hole phase, but you cannot combine them in a useful way to reconstruct a wormhole. So
that's not. I mean, you have only 1 copy, and you're looking at a subset, and then constructing.
Yeah, I understand. I'm giving an example. I'm saying that the fact that you can do this algebraic doubling of the operators does not necessarily mean that the correlators of these operators will have the right form, so that you can reorganize them as local bulk fields on a gravitational background. That's what I'm saying. So I think this construction can be done even at small Toft coupling, probably. So where you do not expect to have any kind of space-time in the bulk. I mean, semi-classical space-time.
Sorry, can I come back to this apparently controversial question about the state dependence of operators in the exterior? Because that's something we can certainly do calculations about. So the types of explicit constructions depend on things like the mass of the black hole and so on.
Yep.
Which,
well, no, the claim is that once you include the 1/n corrections, that if you change the state, then those corrections resum to change the leading order smearing function.
Okay. No. My question is, operators in the black hole exterior, they clearly, the way they're currently defined, they depend somewhat on the state, at least on course probability.
No, not if you include the 1/n corrections. Then they don't.
They're linear operators. Yeah. When you for the purpose of this discussion, whenever you say state dependence, you're saying nonlinear operator. That's what he means.
But sorry, Joe. I mean, but nobody has written down the formula where this resummation of the 1/n corrections has been demonstrated, right?
It's been checked to a couple orders in some paper by Mike Duff from.
Okay.
So it's not. In electrodynamics, it's true.
It's very, very different from what you're doing.
I agree. But I don't want to insist on this point because I think I agree with you that it's quality.
And you shouldn't conflate them.
I didn't. I just said that I'm. In my opinion, there is not a conclusive statement about the exterior. That's all I said.
It hasn't been shown fully explicitly. I'll grant
you.
But
I mean, what would even be the statement? Because if you want to make a statement that you can define an exterior operator independent of the state, then
that is
normally it's small perturbations around black holes of a given mass.
Right. No. You define it using the dressing. So you say where it is using the dressing geodesic from the boundary. Yeah. That's the thing. So from at least if the path integral makes sense, which it should to all others in perturbation theory around any background, you can stick that into the path integral in various backgrounds, and it's always well defined. Now, the claim is that in perturbation theory around a particular background, you have 1/n corrections. But now if you change the background, you stick the same formula into correlation functions, and now there's a subset of diagrams you have to resum, which just gives you the smearing function in the new background corresponding to the new state. But it's the same formula you stick.
It's field dependent, it's not state dependent. They're different levels of quantization.
It's the same formula in terms of CFT operators in either state. It's just you can rewrite the formula in a way that's more natural, depending on the mass.
Okay, I think we will disagree a lot on what follows. So maybe, I don't want to insist on this point because I'm happy to accept that the exterior may be defined in a state-independent way. So about the interior now, so the main objection is, or the main question here is whether this is consistent with quantum mechanics, and two classes of let's say, situations where we could run into a problem, which have been emphasized. One is when we consider linear superpositions of states in a single conformal theory. So the question is, if these operators depend on the state, what happens if you take linear superposition of 2 states? And what happens if you entangle the CFT with an external system? And in a recent paper, we checked several examples and tried to argue that there is no observable violation of linearity of quantum mechanics.
What does that mean? Observable for who?
For the bulk observer or for the boundary observer? I mean, the boundary observer is just using the CFT operator, so there's no.
The person who's simulating the CFT certainly sees a violation of the linearity.
In what sense?
Mechanics.
In what sense?
Well, they could study the system in different states, and they use the operator they use is nonlinearly dependent on the state.
But it's like saying that
a violation of the linearity of quantum mechanics.
No, I don't agree with that statement. I mean, you can also look at, for example, the entanglement entropy or something like that, which is not really a linear operator.
No, but that's not an observable. So
Yeah.
an observable is
Yeah, but we're not saying that the boundary observer can necessarily observe the interior directly, right?
But sorry, can we try to keep this at a level that's useful for the majority of people here?
Sorry. Okay, so we have some disagreement with Don and Joe about a certain class of states. Well, the states that Joe mentioned 2 weeks ago, which means states which may be physically orthogonal but mathematically parallel. And if those states really exist, then we would have to perform additional checks of this linearity and consistency. But we believe that these states do not really exist. I mean, they do not really have these properties. But okay, we have to settle this issue. So maybe I will postpone it for now.
I mean, I realize you probably don't want to go into a long discussion about that lower paragraph right now. But I thought last week you told Joe about our calculation.
No. I said I agree with the estimate of the measure. So what I'm saying is what I do not necessarily agree with your calculation is whether these states are excited. The states that you were talking about. So you get a new...
I think this is a discussion we should have offline.
But could you explain what the first paragraph there?
This one?
Yeah. You say that a lot...
Yeah, so a little bit...
Take an example like this.
Yeah. So a little bit, in a few slides ago, I said that if you take a small number of states, it is possible to promote these operators into global operators acting on the union of the two states. And you can do it for 3 states, 4 states.
Small just means small compared to e to the n squared.
Correct.
So anything.
You have to know which small number of states you're going to be trying to...
Yeah. You cannot do it in a way which... yes, of course. Yes. So you first have to tell me which states you're going to use for your experiment. Let's say psi 1, psi 2, up to psi k. And then within the subspace generated by the states, I can define a single linear operator which will have the right properties.
I mean, I really want to emphasize here, though, that the way ordinary measurement theory works in quantum mechanics, you prepare your measuring apparatus first, and then I can...
Yes, but in this case, right, but in that case, go ahead.
I mean, and that's essential because the measurement process in quantum mechanics is usually described as a unitary operator.
Right. On the other hand, this guy who is falling into the black hole, the measurement apparatus will also be part of these operators, probably, right?
Yeah. Although, I mean, can I make it out of the informal?
Yeah, I'm not sure if you can do that. Yeah, I know you said that you can do that, but I'm not sure. So, okay. All right. So there is some disagreement here, but let me now mention a few new results. One of which is some evidence for state dependence based on the eternal black hole in ADS. So,
can you just give a mathematical definition of state dependence? I'm really confused by what this phrase is.
Yeah. So, okay, I will kind of summarize. Okay, so you start with a black hole microstate that you want to study.
Can it be a microstate of something else?
His Hilbert space is state dependent.
Yeah, precisely.
Okay.
The Hilbert space is...
So that's not typical, and they could obviously raise problems for quantum mechanics where you have one.
What is the mapping? So I can have operator in the same Hilbert space, and for other state I choose to name this operator differently. Is that the case, or is it?
I mean, I think the best way of saying
These are functions of states that give you states, but they're not linear functions of those states. So the Kyriakos is interested in a special class of these functions. In general, there's a huge class of these functions, right? You put in a state, it gives you out a state. There's a huge class of these things. Kyriakos is interested in a special subclass of that more general class. But state-dependent operators is a term which has come to mean this more general mapping between states, which is not linear.
Well, I think you can just say that in ordinary quantum mechanics, if I have an apparatus that measures some operator in state 1 and another the same operator in state 2, then it will also measure that operator in any linear combination of those two states. But here he's saying that with the same apparatus, if I prepare the system in state 1, I measure one operator. If I prepare the system in state 2, I measure another operator. And if I prepare it in 1 + 2, I measure yet a third operator.
Yeah, but I want to point out that
This is not in combination with quantum mechanics, right? You give me an state.
You fix the apparatus. You fix the apparatus.
Sorry, but the apparatus is part of the system, right, in this case. So the infowing observer is part of the system, right?
Projection operator.
No, his aren't, because projection operators are
linear
operators.
Requires an overall Hilbert space, perhaps, to do what you're saying. So roughly speaking, you're saying, well, except for measure 0, you can always put things in one Hilbert space.
Yeah, I'm not sure if it's measure 0, but...
There's the CFT Hilbert space. There's one Hilbert space.
Yeah, so there's the CFT Hilbert space, but what I'm saying is that the Hilbert space that the infowing observer will use is embedded in the big Hilbert space in different ways depending on the microstate of the black hole.
I'd like to apologize for the comment I made, which was both confusing and wrong. I'm going to say that your things take in 2 states, right? And they put out 1. Yes. So it's not that it takes in 1 state and puts out another state. You have a reference state that you would like to,
I think that's correct.
Like to sort of have a small Hilbert space around, and that's one of the inputs. The other input is then a specific state. So you have these 2 inputs, and then out comes 1 state.
But I want to emphasize that in low-energy effective field theory experiments, the reference state does not change. That's the reason that we do not have immediate contradictions with this proposal. So let me now give some evidence in favor of state dependence using the eternal black hole. So we know that the eternal black hole is related, in ADS, is related to an entangled state of 2 CFTs. And I think many people agree that the eternal black hole is smooth. It does not have a firewall. So there's some particular choice of conventions where the eternal black hole is dual to this particular state of the conformal field of the 2 CFTs. And now I want to start changing the state. And first of all, let me notice that the thermophile state has an exact symmetry, which is that it is annihilated by this combination, which is related to the fact that it is invariant under time translation with this combination. And this is related to the killing isometry in the bulk. On the other hand, if you act with the operator with a plus sign, then you pick up some phases, and you get a genuinely new state, which in the bulk you can think of as a state that is produced by acting with a large diffeomorphism, which translates both boundaries up or down. Now I want to look at this class of states. I take the thermophile state and I act with e to the I h left times t. So I only do time translation on one of the 2 CFTs. From the boundary point of view, it's pretty clear that this is a new state because it will have different phases when you write this in an entangled state. Also from the bulk, it is clear that this is a new state because you can think of this state as being the result of a large diffeomorphism in the bulk, which leaves the right boundary invariant, but translates the left boundary by a constant amount t. So here I have drawn some kind of nice slices, and I have tried to show how this diffeomorphism acts on these slices. So this is a large diffeomorphism. It maps a state into a new state. And now the question is, if an observer jumps from the right CFT at some particular time, let's say time tr equals to 0, into this state, does the observer experience a smooth horizon or not?
So this is equivalent to the observer jumping into the ordinary thermal field double state at some other time?
Precisely.
And so then the answer is yes.
Good. So the answer is yes, or you can see it from this point of view as a result of the fact that the observer that we have been talking about has been defined in a right relational sense from the right boundary, and the diffeomorphism that we're acting with is trivial on this boundary, but non-trivial on the other boundary. So I think maybe we agree that if you jump into this state, then you find a smooth interior. And if you believe the previous arguments, this will be true for all t, even if t scales like the exponential of the entropy.
But I'm confused by your statement that from the bulk point of view, this is a different state. I mean,
what
you made very clear in your paper is that it's actually the same bulk state with different coordinates.
Well, it's like taking a black hole in ADS and acting on it with a boost. When you get a boost in the black hole, it's a different state. It's a large diffeomorphism which acts on the boundary in a non-trivial. Yeah.
Okay.
Right. So this is not a gauge transformation. It's really
Can have symptotic symmetry.
Yeah. Right. So now we have a class of states labeled by capital T, which all of them have a smooth interior. And this T can be exponentially large. So we have really a very large number of states. So I will try to argue now that this is possible only if you allow state dependence. So equivalently, we will assume that this smooth interior can be reconstructed by state-independent operators, and we will run into a contradiction. And this will be used as an argument in favor of state dependence. I have to say that similar arguments, but probably with different conclusions, have been pointed out by Aaron and Don. I guess the conclusion is different, but please correct me after I finish
my conclusion, at least for your argument, will be different too.
Okay.
It would be the same as the conclusion in your paper?
Pretty much.
All right, so then maybe I should try to hurry up a bit. So suppose that there is an operator n, which is a global linear operator defined on the Hilbert space of the CFT, which measures how many modes we have on some particular, let's say, how many excitations we have on some particular mode for the infalling observer.
Just the right CFT?
Yeah, which is defined relationally from the right CFT. I do not care where this n acts on the full Hilbert space. The only thing I care about is that it has been defined relationally with respect to the right CFT. So I'm willing to allow this n to act on both Hilbert spaces. But yeah. So the fact that all of the states are smooth can be expressed by this equation. So the infalling observer does not see any particles for all t. Now you insert you expand out these time-shifted states in terms of the basis of energy eigenstates, and you get two terms: the diagonal term and the off-diagonal terms. These are time-dependent. Then, as usual, you take the long time average to kill these guys, and you are left with a statement that this number operator on pairs of energy eigenstates has to be 0. So we conclude that at least most of these pairs of eigenstates have to be smooth, according to the observer jumping from the right side. Now, already at this point, it's a little bit strange to claim that the states EE are smooth, while the states E are singular, because here there's no entanglement. So how could one CFT possibly know about the existence of a second CFT if there's no entanglement? But we can make this argument a little bit more precise. So we will additionally demand now, as a condition, that if there is no entanglement between two systems, there should be no wormhole.
That's the only step in your argument I don't agree with.
Right.
I would instead accept the conclusion you came to in the paragraph above.
Good, very good.
Sorry, is wormhole different from just there's a smooth infalling experience from either side? I would have thought it's different.
Here I'm making a very strong statement that there is absolutely no wormhole. I don't care if it's geometric or not. Here is the technical. Let me read the technical statement. That the technical statement of this paragraph is that for any unitary acting on the left CFT, even if it's an incredibly complicated unitary, I want this unitary to commute with this n, with the operator which has been defined relationally from the right boundary. So in particular, if I change the state by acting with a unitary on the left, I don't want to change the experience of the right infalling observer. So so this guy jumps from the right CFT, and I want to say that no matter what you do on the left CFT, you will never modify the experience of this guy, even if you are willing to act with complicated operators on the left CFT. So if you now demand that there's no wormhole, then you get a condition that even if you evaluate the number operator on these states where you have modified them with this unitary, the result will be 0. And this means that you can select this unitary to map the state E into any other state E prime in the CFT, and then you get a conclusion that all states of the form E prime E are smooth. There's no need to be this E and E prime can be different. Yeah. And then basically this is too strong a statement, and you can easily show that you can repeat the counting arguments to argue that this is inconsistent.
But then you're really just relying on the original arguments, right?
Yeah.
I mean, because otherwise, let's just have them be
I'm relying on the original arguments. What I want to show is that it is inconsistent to assume that these operators are state independent.
I mean, that's what they already argued, right?
Yeah, but now we're talking about the eternal black hole. So the summary is the following. We assume that the eternal black hole, as well as the time-shifted states, are smooth. Moreover, we assume that the interior operators are state independent, and we run into a contradiction based on the arguments of AMSES and MP.
Wait, you made another assumption. Sorry.
And there's no wormhole. That's right. There's no wormhole. And there's no wormhole for states without entanglement.
But that's okay. One might have worried already that was inconsistent with linearity. If you think that if the thermal field doubles the wormhole and it's the superposition of these other states, and if it's impossible to affect one side in any of those bases of states, then how can you possibly have a wormhole in the thermal field double?
Yeah, I didn't use the linearity of quantum mechanics anywhere, right?
That's not what's state independent.
No, I'm saying that if you assume that the operator is state independent, and if you demand there's no wormhole, then you get into the contradiction.
There's a question with that.
Yeah, I think when you go to these large times that you want to go, there's some arguments that you can make that black hole horizon is not smooth anymore.
Okay, that's another logical possibility, to find a mechanism that these states become singular after some large amount of time. But maybe we should discuss it later, but I think that it will be very hard to find a mechanism which is actually consistent with the Killing isometry of the thermal field. The thermal field state has a Killing isometry, right? It's an exact statement. It's this statement. It's an exact statement, right?
Well, even for the eternal black hole, if you start having operators at very large times, they're not going to give you...
Yeah, but we're not computing a two-point function between two different times in the same CFT, right?
It doesn't matter. I think you just have effects. The effects that you were talking about, I think will come in.
From the right CFT, the only thing we do is we throw in an observer. We don't want to compute any two-point function between this observer and anything else.
But how do you compute the operators that describe it smooth?
Yeah, I don't want to compute them. I just want to show that they do not exist. I don't want to find them. I just want to show that they cannot exist as state-independent operators. And I gave you a formal argument. I think I'm already maybe over time, so maybe I should summarize. Okay, so this seems to be, in my opinion, strong evidence for state dependence. So the logical possibilities I can see is that either you have to admit to accept that the eternal black hole has a firewall, or that maybe there's some other modification of it. For example, maybe you can declare that the bulk theory is not equivalent to the two entangled CFTs. There are some superselection sectors which play a role, or you can just accept that there's state dependence.
Well, I guess this is heretical, but you could also just accept that the thermal field double doesn't have a wormhole, and it's just two entangled wormholes in separate. But that's not.
Oh, you mean that there are two disconnected?
There's two quantum gravity theories.
Sure.
This was Jonathan Wall's other super selection sectors.
Okay, but
you could just say that's the only super selection sector. There's just never wormholes from entangled.
Okay, so I guess I should try to summarize in 5-10 minutes or so.
Yeah, we can take a little more time. What else?
So let me mention a little bit how these developments are related to the story of ER-APR, which was proposed by Malethina and Saskind. I guess you all have heard about it. It's a statement that if you have entanglement, you have wormholes.
I'm sorry. Can you go back for one moment? So this particular state dependence you suggested in this particular class of states was a rather simple formula, which you didn't write here. Would you mind writing that formula? Because I think that formula is clearly correct.
I'm sorry.
And if that, you had some formula where well, I don't remember.
So
it basically depended on this time shift parameter T.
Yeah.
And the formula you wrote basically followed from the statement that this time shifted thermal field state was related to the other one by the asymptotic symmetries.
Yeah. Can I say?
So that formula was clearly right, and if
Yeah. So the point is
that we call that state dependence. Anyway, that thing.
I mean, maybe let me make a comment on that. So the way I usually like to think about this is that we fix the t equals 0 state and consider jumping in at different times. Now, if we think about it that way, then we're just studying Heisenberg operators at different times, and those are different observables. And there's no rule. I mean, that's not state dependence. The fact that if I measure, the x operator at time 0, or I measure at time t,
I don't think I agree.
Those are different operators.
I don't think I agree.
call that state dependence.
I think that's not all we have here. But, okay. Can I try to summarize this ER-APR story and maybe mention one more thing, and then we can come back to this discussion. So here, the question is, what happens if we have two systems which are entangled, right? So if we take the CFT and we entangle with another system, how do we reconstruct the interior? And there are, some classes of situations we want to consider. One is when the small system is a simple qubit. It's a small system, so the entanglement is order 1. Or the situation where it's a large system, and then which could be the same CFT but in a generic state where the entanglement is not special. Or it could be the same CFT in a special entangled state like the thermofield. So how do we describe the interior in all of these cases? So I will try to give you a very natural generalization of the previous rules, and I will try to argue that they reproduce expected physics as, let's say, predicted by the ER-EPR story. So in this case, when we have two systems, we have two algebras. One is the small algebra of simple operators in the original CFT, and then AS is the algebra of operators in the second system. Now we consider the product of the two algebras. And for now, what we call the small Hilbert space, on which we will define the interior and effective theory, is defined as the span of states that you get by acting on psi with all possible operators, either from CFT or from the other system. Now, this space may or may not be larger than the space that you get by acting just with operators from the CFT. For example, in the thermofield state, because the entanglement is so special, these two spaces are the same. For other states with more generic entanglement, this is a bigger space than that one. Now, so in general, this space that you define by acting with all possible products of operators from two sides can be decomposed into a direct sum of subspaces, each of which is closed under the algebra of the single conformal theory.
Is that unique? I think it's nowhere close to unique.
Well, if we talk about the states of the type that you have been that you mentioned the other day, yeah. So for those states, I agree we will have to think a little bit more. You mean states which are parallel?
I think an old black hole is an example where the outside algebra is larger than the inside. And you think it's possible for an old black hole?
I'm sorry, maybe. So this algebra, if the external system is very big, we will have to truncate it somehow. So this will be a small algebra again in this construction.
Wait, so you can't talk about an old black hole? Sorry.
Limited set of operators.
Limited set of, exactly. Limited
sorry,
set.
so you can't talk, okay.
Yeah. So, okay.
Sorry,
so,
what does closed mean? Is it again with some sort of cutoff, or it really means?
Yeah, no, with a cutoff, of course.
Okay, and the cutoff can kind of depend on the state and the label J, or the cutoff is uniform?
Well, this is a hard question to answer precisely, unfortunately, but I cannot answer your question on it. I mean, I cannot give you a precise answer even for the case where there's no entanglement. So about the cutoff, it's hard to understand how to regulate this algebra in a natural way. So let me just make the statement that each of the subspaces are closed on the algebra A CFT. So what we do is we identify an equilibrium state within each of these spaces, and we define the mirror operators relative to that equilibrium state acting on the subspace H psi of J, and then we take the direct sum of all of them. Okay, since I'm running out of time, let me just tell you what you get from this. You get that if you apply these rules in the case of the thermofield state, you reproduce the statement that there's a geometric wormhole in the sense that you can you can compute these mirror operators, and you find that, the experience of the infalling observer from the right can be affected by the action of operators on the left CFT.
But you don't define mirror operators here, right? Because you already have them. Because they're
they're slightly different. They're slightly different than the other guys.
But I mean, here there are simple operators that are
not. No. I mean, these mirror operators are not the simple operators on the left CFT.
But aren't those?
For example, look at this equation. Yeah. I mean, modulo 1 over n issues. All right. Now, on the other hand, if you repeat the same process for a generic entangled state, then the Hilbert space that you get is, in some sense, the square of the Hilbert space that you get from a single CFT, and you reproduce something that looks like that. So this Penrose diagram, I think, has also been drawn by Douglas and.
We should put question marks there.
Yeah, yes. So the statement here is you define the mirror operators for this side, and then you reconstruct a smooth interior. If you want, you can do the same thing from the other side, but they don't communicate. They don't communicate within effective field theory. So there's no short geometric wormhole. However, you can show that if you act on this CFT with arbitrarily complicated operators, you can still affect the experience of this guy, which means that, in fact, there is some sort of long non-geometric wormhole. Or in other words, the mirror operators of tilde relative to this state have support on the other system. Okay, so let me just very briefly mention a toy model in ADS, which is work in progress. Now, let's forget about black holes and try to do a similar construction of mirror operators in empty ADS. So we take the CFT on the cylinder, and we consider a time band which is short. So this is different from what we had before. In particular, the length of this band is taken to be less than the light crossing time of ADS. If you look at the bulk state, there's a coastal diamond in the center of ADS, which is space-like relative to the time band on the boundary. So as you make this longer, the diamond gets smaller, and if you make the time band longer than pi times r, there's no coastal diamond in the center. Right? Now, operators inside the diamond should commute with local operators in the CFT in this time band up to Gauss law tails, which have to do with the gravitational dressing. So two questions that have been that are relevant here is one is that this gray diamond seems to be behind the horizon for an observer who is confined to move in this causal way, in this part of the diagram. So could we take this as a toy model and try to define mirror operators for the interior of this diamond in terms of operators acting on the time bound in the CFT? A related question, which was discussed previously in the meeting, is the following puzzle. If you take an operator P in the center, naively it seems to commute with all local operators in the CFT from bulk causality, but then there are axioms in quantum field theory that then this operator should be proportional to the identity. How is it possible? And I want to present what is, I think, my intuition at least, that is a question about simple versus complex operators again. So if we act with an arbitrary number of local operators within the time band, then in some sense we reconstruct the entire algebra of operators of the conformal field theory, and obviously there is nothing that commutes with all of these operators apart from the identity. On the other hand, what bulk effective field theory requires from us is not that this point at the center commutes with all operators, but only that it commutes with operators inside simple correlation functions of the local boundary field. So in that sense, we again can define this small algebra of acting with single trace operators on the boundary, small number of them, define a small Hilbert space, which is like the code subspace that we heard about. And because the ground state of the bulk theory is entangled, it's very natural to expect that this Hilbert space will contain states which are excited inside the diamond. So this is like a bulk version of the Riesz-Leader theorem. And we would like, this is something which is in progress, we would like to understand how we can define mirror operators in this particular case, where there's not even a black hole, and see if we can reconstruct this point by the method that I presented before. Now, these mirror operators will approximately commute with single trace operators within this time band, but if you take extremely complicated combinations, then the commutator will be manifestly non-zero. So in some sense, this is a toy model of complementarity, even though there's no black hole. Let me also mention that this may have some interesting relations to the discussion about precursors. So if you take this point, another thing you can do is do simple bulk evolution and relate it to a single trace operator later in the CFT, which you can then map back inside this time band using the Hamiltonian. So a natural question is, how is if we find this mirror construction for the interior, how is it related to the construction you would get by the precursors?
What was your comment that using extremely complicated combinations give a non-zero commutator?
Yeah. So I said that if you have an operator P at point P, okay, of course it does not commute with a stress density tensor on the boundary. That's one thing, the gravitational dressing. That's one.
Depends how you dress it.
Right. But apart from that, I'm saying that if you look at n squared point functions, you have no reason to expect that this operator P will commute with a boundary correlator. Boundary operators. Okay, so let me summarize. I tried to argue that reconstructing the interior is an outstanding problem in ADS-CFT, and I proposed a method which is based on the mirror operator construction, for which state dependence plays a key role. Thank you.
Any other questions or comments?
I want to just comment on how I think about the background dependence of HKL, anyway, which is not so much that there's a 1/n expansion that converges kind of globally, but it's more like a continuation where you, given the construction, say in the ADS background, you build a region of that, including time-dependent backgrounds. You go to the edge of that region, you build it further and further, and you ask what kind of natural boundary would stop you from extending the construction of the walk operator. And the only natural boundary that I know of is a black hole horizon. That's the only one that's come up. So that's sort of the argument, I mean, that I would give that construction gives you a globally defined linear operator. Okay.
So it seems to me that the existence of these mirror operators is necessary but not sufficient for a black hole that is smooth interior. You agree with that?
Yes.
Okay. Do you have you thought about?
So to clarify, the statement is that the algebraic steps that I followed can be applied to any chaotic statistical system, right? But it doesn't mean that it has something like a geometric interior.
Right. So, I mean, have you thought about making a connection between these mirror operators in the CFT and the physics inside the interior? You know, like a first principles sort of dictionary.
Between the interior of the black hole, you mean?
Yeah.
Well, the only thing I can say is this formula that you take the bulk expansion of the field, you just do gravity, semi-classical gravity, you write down the expansion of the field, and then in semi-classical gravity you have some creation and annihilation operators, and you identify some of them with the mirror operators.
But the input to that identification was just that it gives the answer you expect, right?
Yeah, all right. So one thing I would like to understand better is maybe, I don't know if this is what you're asking, but I would like to understand better the measurement theory for the infalling observer in the sense that we would like to find some maybe more dynamical principle which allows the observer to uniquely identify these particular operators as he or she is entering the horizon. But we don't have anything concrete to say about that.
I mean, it is true that in some cases you can define operators which do reproduce like effective field theory and thermal field double background to all orders in 1/n this way. I mean, there are various problems with that, but that you can do. There are other problems, but that you can do.
Yeah. So given the state, you know what correlation functions you expect to find.
Yes, I mean, in some sense you're putting the answer in, but it's not totally trivial because you don't get to fiddle with the operators outside, so you have to put in the answer in a way that's consistent with the operators outside.
Yeah, I agree. It's not trivial that these operators exist fulfilling these criteria, but that doesn't tell you that you're correctly capturing the physics as you fall across the graph.
Well, maybe let me ask a question related to that. Like, this is a construction of a smooth interior. It seems like I could have done the same thing to make a construction of a firewall, right? Where I define the tildes with a state.
Fine. Okay, so you could define, for example, a state where it has a shock wave coming in from the inside, right?
Or even worse than that. Just in your definition of the tilde operator, I could have put a phase so that like it's some infinite energy state. And then I would have declared that I had constructed a firewall.
Right, so I think it depends. Are you going to demand that effective field theory is obeyed in the interior, or you're going to give it up completely?
In the interior, I mean, the question we're trying to resolve is whether there's some infinite energy state at the horizon or a firewall there. So we're not allowed to assume that one way or the other. And then the approach you're taking is asking whether you can define a set of these operators such that you have certain properties.
So I think you can define them so that the interior is always singular.
Right.
But you cannot define them in such a way that the interior is smooth, but there's just one particle. That's harder, right? Because this particle will form the singularity. So just to keep it there. I mean, if effective field theory, you want to destroy the interior completely, right? Right. So what I have given you is, I have shown you that it is possible to define these operators. I have not given you an argument for the uniqueness. I agree with that. So it would be nice if we could understand how, this observer is part of the system. He wants to perform a measurement while crossing the horizon. So it would be nice to understand how these operators are selected dynamically by the experiment. But we do not have anything concrete to say about that. So I agree with you that it would be nice to make the choice of these operators more, to demonstrate their uniqueness. Yes.
I have just a technical question. I don't know this very well, but from what you explained, your mirror map is just a Tomita operator, J, that was defined in 1972 or something, which depends on a choice of state. C, I mean, it has to be separating or for some technical. But how? I didn't understand how it depended on your sort of choice of small algebra, because
that's one of the annoying things that.
Algebras, not small algebras.
Right. So this is not right precisely. So what we're doing.
I mean, I'm not saying what you say is inconsistent.
No. Yeah. So what we're saying is, yes, I understand. So in the Tomita-Takasaki story, the algebra is a proper algebra, so it's really an algebra.
Yeah. So
here we have
J depends on C. Called. So how does the choice of your selection of local operators?
That's this comment. That's one of the annoying things, that we do not have a very clean, let's say mathematically clean way to regularize this algebra. So it has to be done based on some physical intuition. So you have a large n-gauge theory. You take a small number of operators relative to n. You have to smear them in time a little bit. So I think you need some physical input. I'm not sure if there's a clean mathematical way to regulate this algebra. So it's like asking when is the large n expansion reliable? Okay, we know it's reliable when the number of operators is not too large, but can you make it very precise? Can you really separate correlation function in CFT into those for which factorization works and for those which doesn't?
You can just, at a clear level, you can just say you have some number of linear equations that you're solving, and you just want to make sure that it's not.
Yeah, but this number has to be finite, and the question is, how do you select this cutoff?
Yeah, but when you do the cutoff, you can then count the number of.
Yeah. But then there are many ways to select the cutoff.
On the right side,
right.
So then you have to get unlucky to not be able to find a solution.
Right. But if we want to understand, for example, the one over n corrections that you have been asking about, it would be nice if this coarse graining of the algebra could be made more precise.
Yeah, I agree with you. I'm just saying at a technical level, it's not crazy to think rotillas exist, because he defined them by saying that they obey some set of linear equations.
Yeah, so I don't say they don't exist, but how do they depend on the choice of your system of operators? Can you say that?
Yeah, so
the Tomita operator does not depend on any choices except for the state.
Yeah, because in that case you really have an algebra, you really have an algebra.
Right, but so setup seems to be somewhat different.
Yeah, so this is a realization, right? So I think that this is a good question. What is the mathematical formalism that is able to deal with this type of situations where we have approximate algebras? It's clear from the CFT that there is some kind of approximate algebra because of the large n hierarchy between single trace operators and the black hole states. But I do not know any, let's say, precise mathematical formalism which is able to deal with this approximate Tomita-Takasaki story, if you want.
This approximate algebra does not depend on the state.
It does depend on the state. I don't know. It depends on what you mean by that. It does depend on the state. In this Tomita-Takasaki story, sometimes there's another state dependence that you may be thinking about, which is about the choice of state within this Hilbert space A of psi.
Yeah, but you also have a state dependence of the algebra, let's say, somehow.
Yeah, in this case, we also have a state dependence on the algebra, perhaps, because we have to regularize the algebra somehow.
No, but the algebra is just the low energy, low dimension operators. It's basically independent of the state.
Yeah, this type of regularization is independent of the state.
Okay. Well, I guess we should wrap it up. Thanks again.
Thanks.